You're not worried. You have to make sure you don't overconfident to be comfortable. Yeah, man. I know how the system works. Away goes with everything. But why is it two? Like what happened to PSG.
Exactly. Training. So I don't want to
That doesn't look very sharp. It's blurry. Is the camera clean? No piece of tissue. Sometimes the camera. Actually, this looks sharper though. Yeah, it looks sharper. You don't have anything? The thing is actually it doesn't look so bad here, so it may just be the way it gets spun. Yeah, but yeah, it's just show me. All right, good afternoon. So we're on to our last topic in the subsection of graphs, and I guess I should announce at this point that, hold on, is Good Friday next week? Okay, right. So you need to have your quiz too. But when would you prefer it? Good Friday to Saturday? Saturday to Sunday? Tomorrow? I thought I heard somebody said tomorrow. Huh? Is quiz 2 online? Yeah, well, how else would you take it? Sorry? Good Friday to Saturday? Well, this is why normally we put it on the weekend. Normally you would get like a 30-hour stretch, so it would be like Friday to midday, Sunday or something like that. But I was concerned that some of you might have issues with doing your test on Friday. On Good Friday, sorry. Thing is, if there are no objections on religious grounds, I'm quite happy to make it the usual Friday to Sunday. It's not 48 hours. It's Friday evening to Sunday afternoon. Not hearing any here. So, all right. So, sorry. That's what I'm saying. The proposal would be that it would open on Friday evening and close on Sunday afternoon. Sorry? Afternoon as in close to 12. You get, I think I usually give you 30 hours, 30 something, maybe 36 hours. Yes, I'll open the practice just like, yeah, I guess if I can remember from today. Not tomorrow. So the topics include everything up until what we're doing today, which is why I couldn't open it before today. But if there are no objections on religious grounds, I'm quite happy to open it for that window. Those of you who are Saturday worshipers, just start on Saturday evening. Those of you who are Sunday worshipers, you probably don't have a problem doing it on Friday night anyway, or Saturday. And those of you who don't don't believe in any of that, then you have nothing to you. Just another holiday. But I didn't know if anybody was going to have an issue with that. So, all right. So, okay. Barring any objections, I will set the time. I'll set the time on the platform. You'll see it. What date is that? 15, 22nd. 19. All right, and the practice quiz will be open as soon as I remember to do so. All right. It also means that there's no POTW next week. So I am still adjusting 9, and if I'm by the end of today, I'll just give it the other one. I was kind of holding it back in case there had to be a bonus POTW. But I don't know. I'm not really hearing strong calls for bonus POTW. So maybe. So then. So, all right. So I'm still building the problem that should have appeared as the replacement for the originally planned problem, which is why I haven't seen the second one yet. I'm gonna give myself an expiration date of today, this evening. So push comes to shove, one way or another, you'll have the second one. If it looks remarkably similar to the first one, you'll know that I failed with my replacement problem. But it also then means that you may be in jeopardy for a bonus POTW, because I may not have any problems left over, quality problems left over to warrant a bonus POTW. But anyway, we'll see. I didn't hear strong calls for it, so maybe it's not even possible anyway. And maybe you're good with your POTW scores. All right, I'm going to. I think that takes care of my announcement. So let me get started with the lecture content itself, and then if there are any more questions, we can deal with them afterwards. All right. So, well, one more category of graph problems to discuss, and that is the problem of you're given a graph, two distinguished nodes. You can think of one as a source, and that one as a destination. And the question is, what is the shortest path? And now this way, when I say shortest, I mean lightest weight path. So taking the weights into account, shortest path from the source to the destination. Question? You were sleeping? Huh? She wasn't here. Okay. We just spent like 7 minutes discussing that. All right. So what happened now? I just got derailed. What was I saying? Single source shortest path problem. That's what that problem is called. So you're given a graph. It's actually usually a weighted graph. I didn't say whether G is directed or not. That's optional. So G may be directed. It's the same algorithm, regardless whether it's directed or not. So that's what the problem is. You're given a graph and two distinguished nodes. You want the lightest weight path from one to the other. Yes. Yeah, G equals angle bracket V comma E. Yeah. There's a smudge on it, so it may have confused you. Let me straighten that up. That better? Okay. So yes. So the question is, how do you solve this problem? And remember, this problem, as described, is sort of making it sound like it's something to do with some kind of geography, points in space, and trying to find path, as in a physical path. But remember, graphs are abstract things. So what the nodes represent, so you should think, when you see this kind of problem in this generic form, you should remember that it's far more general than just physical paths between places and points in space. I could be asking about the number of operations to convert a number to another, for example. I could be asking about how many moves in a game to get from one state to another. I could be asking, you look at a chessboard and you see start state and you see some final state. I could be asking, what's the fewest number of moves that it would take to get from the start to the end? All of those are examples of single source short path problems from the graph context, okay? So it doesn't have to be physical movement. Right, so that's the problem. Now how do we solve this? As in, what algorithm? There are multiple algorithms for this. One of the most popular ones is called Dijkstra's algorithm. That's how you pronounce that name. Yes, I believe you is Dutch, and that's why that J gets pronounced like that. It's good only for certain kinds of graphs. And thankfully, that's the only kinds that we're going to talk about. But there is another category of algorithms called Bellman-Ford algorithms, which are more general than the Dijkstra's algorithm for solving the shortest path problem. And sometimes you might want to know, for arbitrary pairs of nodes, what's the shortest path between them? Then that's not a single source shortest path. You might want to solve what's called an all pairs shortest path. And there's an algorithm for doing that that's faster than doing Dijkstra's n times. Okay? So, just kind of giving you a brief overview of the different kinds of shortest path solutions there are. But we're going to focus on Dijkstra's, and it has a restriction. So, if for every edge the weight is positive, I suppose you could use equal to 0, 2. Then we can use Dijkstra's algorithm. I'm going to abbreviate this. This is the SSSP. Right, so let's talk about the idea of how this works. It's that recursion idea again, that wishful thinking, even though the implementation is not necessarily recursive, but the thinking about why this works, that recursive wishful thinking idea really helps. And here's the general approach. If I want to find, so here's the idea. Here's node S. And this cloud is supposed to represent the graph. Over here is node T. And now what I'm going to do is look at the neighbors of S. Let's say that for illustrative purposes, I'll be definite and sort of indicate that it's a directed graph. So here I have all these possible first steps to take from S. And I don't necessarily know which of those is going to lead to the shortest path to T. But here's a general idea. It must be the case that the shortest path to T must involve shortest paths to all the intermediate nodes on that shortest path. Say that again? Or is that obvious? Shouldn't be obvious. Let me say it again. Suppose you magically knew what the shortest path from S to T was. One thing we can say for sure is that if you examine all the nodes along that path, the path from S to each of those must have been shortest. Why? Suppose you have some arbitrary node in between, V. And I tell you, the shortest path from S to T involves this V, goes through this V. And now I'm asserting that S to V must have been a shortest path. If that is not true, that means there's a shorter path from S to V. But then you could just replace the one I gave you and make the path to T even shorter, don't it? And so that's why it must be true that every node along the way must have been, that node that I selected, the path to it must have been the shortest path to it from S. What that therefore means is that I'm going to then want to have to find the shortest path among my neighbors from S. Now, because I don't know which of those is going to necessarily lead to T, it doesn't necessarily mean I always take the lightest one from S, that will necessarily be the one that leads to the shortest path overall. What I do know is that if my first step to T, the best path to T is along an edge that's not the shortest, that must mean that the other one that is shorter didn't get to T. All right. Now, the wishful thinking part works like this. If there is in fact a path, so if there's no path, you can think of that cost as being infinity. But if I somehow knew what the shortest path was from each of these, let me call these some names. Let's call this B1, B2, B3, and B4. They're just arbitrary. The shortest path from S to T must involve in other words, so now this is a general picture. So I have an arbitrary intermediate node V. So this is not necessarily an immediate neighbor. If this is a shortest path, then S to V must also be shortest. So then what that means if I'm taking only one step at a time, and this is the idea behind Dijkstra's, is that when I'm taking one step from S, all of these nodes will now be labeled with their shortest paths from S. Because whatever their weight is, that's going to be up to that point, the best known path, best known weight path to that node. The lightest among those would be confirmed as the shortest path to that node. Understand what I just said? So we're going to maintain, it's sometimes called a distance vector, but it's basically just an array of distances where you have an entry per node. And those distances are the best known distances from the source so far. And we're going to perform a kind of exploration, just like a traversal. And what would have been visited in the traversal process, you can think as now being confirmed. We're confirming a distance. So the same process where we would have now marked something visited, that distance that we've had up to that point will be confirmed as the shortest distance from S. Well, the thing, once you visit it, it doesn't get updated again. Only while it's discovered does it get repeatedly updated. So here's the principle. If at this point in the first step, S would have discovered V1, 2, 3, 4. All of those would then get labeled with their distance, with their weights. Let me just put some labels on this. This might be W1, W2, W3, W4. Up until this point, what I now know is that the best distance so far from S to V1 would be W1. The best distance so far to V2 is W2, and so on. For V3 is W3, and for V4 is W4. I don't know for sure that those are actually the best distances, but maybe something, suppose W4 is 50, and W3 is only 5. And maybe there's an edge from V3 to V4 of only another 5. So if I go to W4 via V3, then maybe I only pay 10. So the distance could improve as I discover more edges. Yes? So in the first instance, when we go through that discovery process, nothing is confirmed yet. So right now I'm visiting from S, if you want to think of it that way. I'm exploring from S. S gets marked visited because essentially I know the distance from S to S. That's confirmed to be 0. But what happens next? I now have best known distances to those neighbors. Now among those, and this is where the part that looks just like the other algorithm, among those that are best known distances, if I take the lightest one, that's guaranteed to never get any better. Why? Not only because it's the lightest, no other edges have negative weights. So since they're all non-negative, you can't ever decrease the best known distance. You can only hope to add more to it. So if I take the lightest among all the distances known to that point, I'm confirming that that's the best way to get to that node. That makes sense? And that's how Dijkstra works. You keep repeating that traversal process until you visit the destination. once that's the overview, you're going to perform a traversal in the way that we've been discussing so far, where you have a priority queue of discovered nodes. The thing you're going to use for the priority will be the distance itself. So we're going to use the best known distance to our node U as its priority in the priority queue. Let's run an example so you can see this. Yeah? Or that's not necessary. So that's 2. No. Sorry? I get 3. Becomes more interesting than 2. If a 3 was a draw. I don't. Oh, you mean, oh, I saw what you mean. I didn't want that to happen. Anyway, that's fine. All right. Yeah, so one shortest path from V1 to V5, we're going to use Dijkstra's algorithm and see how this works. So we set up our traversal as usual. And now here, I'm going to label the column, I'm going to call it confirm. So you can think of that as being just like visited. I'm going to need more space, so I'm going to have to take that off. Hope you got that already. I'm going to keep track of a source. Uh-oh. Hello? Why was it not plugged in? Hmm? I'm introducing a new column. I'm going to call it distance, because that's the best known distance that we'll have to each node. So that when you don't pay attention, I warned you I was going to erase it. So those discovered nodes are ones that are the distances that are being used for my priority queue, for the priority queue, right? And we're starting from V1. So we'll know the distance to V1. It doesn't really have a source, but we know that distance is 0. And now remember I erased it, but remember that what we're keying the priorities with is the best known distances to each node, to that point. So we do our usual discovery process from V1. What does V1 discover? V2, 3, and 5, right? And we're keying it with the best known distances. Now, if the distance from V1 is 0, then V1 to V2, total distance is now 3. To V3 is 12. And to V5 is 10. What's the usual process again? What's the next step? You're going to remove an element from that queue, which has the highest priority. So the lowest, normally you take the lowest weight because you're looking for shortest path. So we're going to take out this one here that confirms the distance. So now we know that the shortest distance to V2 is definitely 3. We don't know what the shortest distances to the others are yet. We just know the best known so far. To V3, so far, it came from V1 was 12. So V5, so far was V1 from V1 was 10. And now we're going to run our discover process from V2. V2 is now confirmed. We're going to explore from V2 to see if we can get any better distances. So we have to improve some and add some new ones that we didn't see before, if anything. So V2 can see V3 and V4. Now the weight to V3, and this is important, the weight to V2 was 3. The distance to V2 was 3. So V2 is seeing V3 with an additional 2. So that means it's actually seeing with a distance of 5. Because the edge plus the distance to V2. Remember, these numbers are supposed to represent the best known distances from the original source. So we have to accumulate the path lengths. So that means that we're going to, what we just discovered is that V3 can be reached at a distance of 5. And up until now, the best known distance to V3 was 12. That's an improvement. So we're going to mark that. Update the data structure in our priority queue, so that for V3 we're going to associate it with a weight of 5, and then we'll have to remember that this came from V2 now, not from V1. That's telling us which edge we need to use. Okay, V5, nope, that's not touched by the expression process from V2. The other thing that it does is adds V4. And now we're coming from V2, and the distance is going to be 8. I have 5, you already have 3. Remember that these distances represent the best known distance from V1, original source. Question? Yes? Because these numbers represent the best known distance from the original source, V1. So the distance to V2 was 3, V2 to V3 is 2 more, a total of 5. Right, but now proceed in the same way. You're going to check out the highest priority element. That's going to be this one. Here we have V3 from V2, and its confirmed shortest path is 5. Let's put back orders. V5 from V1 with a weight of 10. V4 from V2 with a weight of 8. Explore from V3. What do we find? Against the V4, what's the new update? 5 plus 2 is 7. V4 was at 8, so that's an improvement. I can see V5 with a 7. 7 plus 5 is 12. That is not an improvement. So we're going to leave that alone. Leave the 10 in there. Up until now, the best known distance to V5 is still 10. But that doesn't confirm that it is 10 because there are shorter distances around. So who knows? Maybe there are other alternative paths to V5 via these nodes that might add up to something less. But we can confirm V4. Explore from V4, the additional weight is 1, so then that is an improvement. At this point, we now confirm it's the only element in the queue. So now we know what the weight of the shortest path is. How would I actually construct a path? So let's write that down. So the weight of the shortest path is 8. The shortest path itself is what? Okay, how would I read out the information from the work I've done? What? You do what? Work backwards. Work backwards from the destination. So how did we get to V5? We came from V4. What was the best path to V4 was from V3. And the best path from V3 was V2. And the best path from V2 was from V1. Never mind the ordering. That was a little accident just because of the way I set the graph up. The ordering of the the index is not what's important here. What's important is the edges that you're reading out of the table. The question up front was the value would still be the same no matter what the order. The reason why I can't answer that, because that's a very strange statement, is that if you change up the order, you may not have edges. For example, there is no edge from 1 to 4. So if you swap the order and put 4 up here, that's nonsense. There's no V1 to V4. You understand what I'm saying? And you can't change the order of the edges arbitrarily because by the nature of a path, it means that. What would be different? Yeah, exactly. If you change up the order of the nodes, then you're changing the graph, or you're violating the edges in the graph or something. Yes? All right. Okay, so the question was, suppose V3 to V4 had been 3 instead of 2. And so in that case, we would have had an 8 in here already. And it would have been questionable whether we should update it to be still 8 or not. Chances are, if we're coding this, we would have said, why would I update it to be the same weight? I don't want to update it unless it's a definite improvement. So chances are you'd code it so that it says if it's strictly less, then improve. Otherwise, leave it alone. In which case, this would not have been gotten from V2 V4 from V2. Yes, indeed. Question up front says, is it possible to have more than one shortest path? And says, yes, absolutely. It's possible for you to have a non-unique shortest path. That's an example. And then what? Sorry? Still the shortest path. You just can have multiple shortest paths. Just like how you can have a tie for first place in a class. You don't then say, well, neither you came first. You say both of you came first. And then there's no second place. Second highest score, third highest person. Okay? Any questions on this? Right, so that's Dijkstra's algorithm. And that is the, well, the bulk of the course. There's still some very deep theory to cover. Not this class.
Oh.
This class, the generic traversal, I just need to talk a little bit about time complexities. Yes. That's a tutorial problem. That's the last problem on the tutorial. In fact, the question asks you to come up with an example of a graph where the edge weight is negative and causes Dijkstra's to fail. But if you understood the principle about the assumption that when I confirm this lightest weight in my discovered set so far, I'm assuming it can never get any lighter because there are no negative weights around. Just think, suppose in this scenario there is well, this problem is that this is V5, that's the destination itself. Here, okay, back here. When I took out 5, because 5 was lightest among these, how do I know that at that point in time, maybe from V4, there's this massive negative weight that would have totally compensated for this 8 and just dropped the total weight to like 1. Then in fact, it's not clear that that this is the best way to get to V3, in fact. You understand what I'm saying? So when we take this and confirm it, we're saying the best distance to V3 is 5. But what if there was this negative weight from V4 to 3 that had -5, for example? Then 8 plus -5 is only 3, which is better than going via V2 with a weight of 5. Question is, what if the graph has cycles in it? No problem. If the graph has cycles in it, what will happen is you will rediscover a node that's already confirmed. But because all the weights are positive, the subsequent edge that you discover it with will only add to something that was clearly at least as large as the distance you confirmed it with before. Okay? All right, so now let's talk a little bit about all these traversals have the same pattern. There's a method to my madness. That's the reason that I write these tables like this for all those 4 algorithms. So depth first, breadth first, Prim's, and Dijkstra's algorithm, you notice that I present them in the same way. And that's because although if you're implementing each one directly, and certainly when they were first invented, they didn't all conform to a single generic scheme. It's only long after the fact when we see all these in perspective and they say, hey, these are actually really similar to each other, that we can even write one piece of code that actually could behave as any one of those 4, just by depending on how you define what the priority is in the priority queue. So I could write one generic traversal algorithm that uses a priority queue, initializes it to nothing. The node you want to start at, put that in the queue, and then in a loop, remove an element from the queue, discover neighbors, add them to the queue with the designated priority. What is that designated priority? Well, it depends on which traversal we're doing. If it's Dijkstra's algorithm, we're going to add the edge weight plus the priority that used to be there. If it's prims, we're only using the edge weight. If it's breadth first, how do I simulate a 5-foot queue with a priority queue? Not all the same. Then it'll be up to implementation to determine the order. Make the priorities increase. So they'll automatically say, make the priorities conform, increase with the sequence number. So the ith element to be inserted gets priority I, basically. And that will guarantee that the later the element comes, the further back it will go into the queue. How do I simulate a stack with a priority queue? Make the priorities decrease. That makes sense? So the later you put it in, the lower the priority will be, so it will come to the front. So, so basically, if you want to simulate depth first traversal with this generic priority, with this generic implementation, you could do that. One thing your priority queue does have to support, though, is this business of modifying the object that you've already put in there. The binary heap that we discussed to support a priority queue doesn't naturally support that. So if you try and implement that, you have to do some workarounds. And there's various ways to try that. But none of them are clean, as in, it's no simple, straightforward thing. You have to create an auxiliary structure somewhere that can help keep track of where the nodes are. Because the heap, remember, it's no use trying to search a heap for a node. And when you want to update something, it's already in there. You have to find it, find out what its priority is currently, and then update it if necessary. Normally, a binary heap or priority queue only supports grabbing the item with the highest priority. It doesn't normally support you asking what is the priority of element X. That's buried in there somewhere. So you have to often maintain your own separate auxiliary data structure that does that for you, so that you can then reference it to find out what its weight is, and then have it help have a pointer into your structure so you can grab it, make the update, and then you have to still change your binary heap implementation so that when you make a modification, so usually introduce a method, a function called update, that given the node, when you change the value of the priority, then it will either bubble up the binary heap if you decreased it, or push it down if you ended up increasing. We had level increase for these. You'd always be decreasing. For these implementations, these applications, you'd always be decreasing the key. So it's basically gonna, when you change the weight, like how we change from 10 to 8, for example, that's gonna cause it to have to go up the tree somewhere. Remember that smaller values are towards the root, right? So that's one of the it's not a limitation, it's a caveat, I suppose. It's an additional step in order to make this work with a generic traversal. So let me try and summarize what I've just said, and then come up with a kind of generic time complexity for all these traversals. So first point is, now based on the implementation of the update that I just told you, it's possible to implement update so that its time complexity is log n. And now, for the analysis. For a graph of n nodes and m edges, the time for the traversal, so this is now any of these, prims, Dijkstras, both breadth first and depth first would fall under the same category, and you'll see, therefore, maybe we don't want to use those, implement those if we know we need those specifically, like this. So anyway, for a graph of n nodes and m edges, the time for a traversal ends up being, now let's see if you can figure out why this is true. So here are the operations I need to perform. I need to do an insert. I need to do a delete min. I probably will need to do a get min to even know what's there. And I'll need to do updates from time to time. How many inserts at worst will I have to do? N, out of n. All right. How many delete mins do I have to do? Also n. And how many get mins do I have to do? Or n. I mean, delete min technically doesn't tell you what's at the front. So if you want to know what our value is, you have to do a get min first. Then you do a delete min, strictly speaking. Of course, when you implement it, you make the delete min return the value just to code. So sometimes you don't necessarily need that separately. But in our strict sense, we will include that as a separate operation. So we need n calls to insert, get min, and delete min. How many? Sorry? How many calls do you think I might need to update? At most m. Very good. Why? Okay. That's an interesting way to think about it. The answer was because you're updating with the edges, and maximum number of edges are m. True, you can't update where an edge is not, but okay. So remember that the number of updates you do per node is different. It just depends how many neighbors a node has. The reason why it ends up being order m is that what you're doing is, if you were to add up the total number of neighbors each node has, that total sum is equal to the number of edges. Remember that? And so that's why the maximum number of updates that you could call is actually going to be order m. Technically speaking, you could even argue why it's at most m minus n, where n is the number of connected nodes and not connected components. Because when you go to visit a node, you're not gonna do an update along that same edge again. So at least one edge is out of the runnings for the update. The rest are still in it. But for others of growth purposes, so this is going to be n times the time for, can I just write, all right, never mind. I'll squeeze it. Time for insert plus the time for get min plus the time for delete min. So that's n times all that plus m times the time for update. That's what we just said. While I was speaking, you were all nodding your head. Yes, I get it, I get it. All I did was write it down. All right. So to summarize, what are these times on an efficient implementation for a priority queue? If you use a binary heap, this is log n, get min is order 1, delete min is log n. So n log n plus time for update is log n, so that's m log n. So the overall time is n plus m times log n. Got that? If you use a binary heap to implement priority queue. If you use a linked list, then that's a different story altogether. What kind of dictionary? Can you use a dictionary to implement a priority queue? A dictionary is an ADT, a priority key is also an ADT. That question don't make sense. You can ask, could you use a can you use a hash table to implement a priority queue? You could, but with a bad idea. Because remember, for a priority queue, you need to find the minimum. How do you find the minimum in a hash table? You have to go scan through the whole hash table. All right. Could I use a red-black tree to support a priority queue? Yes, you can. Sure, you can. All right. All right. So that's it for gaps. I will see you on Friday, and then I'll tell you a little bit about the biggest open problems in computer science. And no, our class on Monday and Tuesday, right? The only reason no class next week Friday because of public holiday. But going hard.
Oh, sir.
Oh, isn't next week your 13th week? Exactly. Who told you that? It's supposed to be 13 teaching weeks. Do you know that most other universities have 15 teaching weeks? And we have to cram the same content in the 13 weeks. I have to try anyway.
Oh, yeah.
Sorry? It is. You needed to have been here. We spent 7 minutes having that discussion. All right, so I'll see you on Friday.
What's the scaling?
Each quiz, yeah.